So I want you to imagine a chessboard, just a standard board.
Right, 64 squares.
Exactly. And you place 1 grain of rice on the first square, 2 grains on the second, 4 on the third. You're just doubling it every time.
Sounds pretty harmless at first.
Right. But by the time you reach the end of the board, you don't just have like a really large pile of rice.
Mm.
You have a mountain of rice that is roughly the size of Mount Everest.
Yeah, that terrifying runaway train of exponential growth.
Exactly. And that is the exact invisible wall we are hitting in modern computing. It's not a physical wall, but you can put a literal nuclear reactor behind our current processors, and when they hit that wall, they crumple.
Which is deeply counterintuitive for most people, I think, because, we are so conditioned by Moore's law, we basically just believe we can engineer our way out of anything.
We just assume, well, faster hardware, more memory, eventually it'll conquer any complex system.
Right. But the mathematical reality is that brute force is completely, utterly futile against exponential complexity. I mean, we're accelerating toward a structural limit of the physical universe itself.
And that limit is exactly what we are tearing into today on this deep dive.
Yeah.
We're looking at this massive, really fascinating synthesis by Sam Castillo.
Yeah, it's an incredible piece of work.
It really is. He's a mathematician who is basically trying to figure out exactly what that wall is made of and how we might literally bend the laws of physics to break through it.
And what makes Castillo's take so grounded, I think, is that he isn't just some ivory tower theoretician,
Right. He has an actuarial background.
Exactly. He has spent years calculating real-world risks in probability, financial mathematics, time series analysis. So he's looking at this entirely through the lens of actual, practical, computational cost.
Yeah, and the methodology he used to put this together is just wild.
Oh, the AI Copilot framework.
Yes. Having completed Google's AI Essentials program, he didn't just sit in a room with a chalkboard. He explicitly used an AI Copilot exploration framework. So he's feeding these monumental concepts through Gemini Pro, Perplexity Enterprise Pro, ChatGPT Plus, and I think Dolphin Mistral was in there too.
Yeah, Dolphin Mistral as well. And he's synthesizing all of these outputs with his own programming. He was coding in Python 3 and C++A and typesetting the whole thing in LaTeX.
Which is just such a brilliant meta approach when you think about it.
Oh, absolutely.
You are using the absolute peak of today's artificial intelligence to map out the structural mathematical death of tomorrow's classical technology. It's poetic.
It really is. And doing that forces us to confront literally the biggest unsolved problem in computer science, the thing that dictates the absolute limits of our entire digital civilization.
You're talking about the P versus NP problem.
Yeah. P vs NP. It sits at the absolute bedrock of complexity theory. I mean, to understand why our computers hit that invisible wall, we have to look at this severe asymmetry between verifying an answer and actually finding an answer.
So, just to break that down for everyone, P represents the class of problems where a computer can find a solution quickly.
Right, and NP represents problems where if you are simply handed the correct answer, you can verify that it is correct quickly.
Okay, let's bypass the textbook definitions here because I want to actually feel what that means.
Sure.
Think about a Sudoku puzzle. We all basically know how it works. If I hand you a completely filled out 9x9 grid, you can verify it in seconds, right?
Right, you just scan the rows, scan the columns, make sure there are no duplicate numbers from 1 to 9, and you're done.
Exactly. Verification is completely trivial, and that is the essence of NP. But if I hand you an empty grid and tell you to construct the solution from scratch, the combinatorial search just completely explodes.
Now, scale that up, because a 9x9 is easy for a computer. But imagine a 100 by 100 Sudoku grid.
Okay, that sounds like a nightmare.
It is, but the verification still takes mere moments, right? You just check the lines. But constructing the solution requires you to place a number, which ripples out and forces another number, which suddenly creates a mathematical conflict, like 50 rows down.
So you have to backtrack.
Exactly. You backtrack, you erase, and you attempt an entirely different combinatorial path. The search space isn't just growing, it is actively multiplying against itself.
Okay, wait, hold on. Let me push back on this a little bit.
Sure, go ahead.
Because I hear a phrase like combinatorial search, and I immediately just think of those massive server farms, the ones run by Amazon and Google.
The supercomputers?
Right. We have supercomputers the size of small cities now. A modern processor can do, what, billions of operations a second?
Easily.
So why can't we just outmuscle a giant Sudoku board? I mean, can't we just brute force guess every single combination in a fraction of a microsecond?
And that right there is the exact assumption that gets completely shattered by what Castillo calls the time to solve metric, or TTS.
Okay, time to solve.
Yeah. This is where the physical reality of time and energy just utterly destroys our hardware optimism. So let's run your exact scenario.
Okay.
Let's assume you have a machine performing exactly 1 billion basic operations per second.
Seems reasonable.
Right. For a problem that scales linearly, meaning we're adding one item to the input just adds 1 unit of time, an input size of 100 takes 100 nanoseconds.
Literally instantaneous.
Instantaneous. But combinatorial searches, like our massive Sudoku or, complex logistics routing, those are exponential time problems. The mathematical notation is O of 2 to the n.
Meaning the time required doubles with every single item you add.
Exactly. So at an input size of 30, it takes about 1 second.
Okay, the processor's handling it, 1 second is fine.
Right. But at an input size of 50, that exact same machine doing 1 billion operations a second takes 13 days.
Wow. From 1 second at 30 to nearly 2 weeks at 50.
Yeah. But then it gets violently worse. At an input size of 70, that computation takes 37,000 years.
Wait, what? 37,000 years?
Yeah. And if you ask that supercomputer to solve an exponential problem with an input size of 100...
Which is the one that took 100 nanoseconds linearly.
Right. That exact one would take approximately 40 quintillion years.
I mean, let me just do that math in my head. The universe itself is only about, 13.8 billion years old?
Roughly, yeah.
You were literally saying a modern server farm couldn't solve a 100-item list if it had been running continuously since the literal moment of the Big Bang.
It wouldn't even be a fraction of a percent of the way done. And that asymmetry is the practical, horrifying face of the P versus NP problem. Better hardware might shave a few seconds off the early numbers, but exponential growth always mathematically crushes hardware improvements. You cannot outmuscle the math.
That is staggering. And, this isn't just about puzzles or Sudoku. Castillo outlines a class of problems called NP-Complete.
Right. The apex predators of complexity.
That's a great way to put it. We're talking about things like the traveling salesman problem, the knapsack problem, the subset sum. And if I understand this correctly, the terrifying thing about these NP-complete problems is that if you find a fast algorithm for just one of them, you mathematically solve all of them instantly.
That's exactly right, if P equals NP.
But how is that even possible? Like, how does a map of delivery cities translate into a knapsack filled with weights? They seem completely unrelated.
It happens through a really elegant mechanism called mathematical reduction. You can think of it as basically building a universal translator for the underlying logic.
Okay.
So when you look at the traveling salesman problem, which is just finding the shortest route to visit a set of cities, you as a human are looking at asphalt and miles and traffic.
Right.
But the algorithm doesn't see any of that. It only sees a graph of nodes and edges with numerical weights attached to them.
Stripping away the physical map entirely.
Exactly. So to reduce this to, say, the knapsack problem, you mathematically force the miles on the map to act like kilograms in a backpack.
Oh.
Yeah, you create an equation that says, find me a combination of items that fits into this knapsack perfectly without going over the weight limit, and you just feed the city distances into the knapsack algorithm as those weights.
So if the algorithm successfully packs the knapsack perfectly,
you take those selected items, you translate them back through your universal translator, and boom, they form the exact sequence of roads for the shortest possible delivery route.
that is wild.
The math underneath just doesn't care about the real-world context. So if you break the lock on the knapsack problem, you suddenly have a master key that breaks the lock on the traveling salesman, on Sudoku, and literally every other NP problem in existence.
Which is, think about the real-world implications of that. Just think about the package you ordered online yesterday. The only reason it got to your door in 24 hours is because Amazon's algorithms are doing a good enough job guessing the route.
Right. They use heuristics. They aren't finding the perfect route. They are estimating because the perfect route hits that exponential wall.
But if P equals NP, and we find that master key, those complex logistics become truly easy to solve perfectly. Shipping costs would absolutely plummet. Global airlines could optimize every single flight path instantly.
The efficiency gains would be genuinely utopian. Hospitals could perfectly schedule every shift and resource. Power grids could balance loads to the milliwatt. We could even cure diseases by instantly calculating how massive proteins fold together.
But Castillo points out the devastating flip side to that utopia.
Oh, yes, the cybersecurity issue.
Right, our entire Modern cybersecurity infrastructure, every single bank transaction, every encrypted message, your healthcare records, relies entirely on the fact that certain math problems hit that 40 quintillion year wall.
Yeah, if P equals NP, every password on Earth is basically an open book.
It's terrifying. But what really fascinates me about Castillo's synthesis here is that he forces a paradigm shift in how we approach this.
How do you mean?
Well, when developers run into a slow program, the instinct is to fire up the C++ compiler, measure the execution time using, say, the ST-chrono library, and try to write a tighter loop.
Right, they try to optimize the code.
Exactly. We assume it's a coding issue. But Castillo explicitly says, no, this is not a coding problem. It's a proof problem.
And that distinction changes everything. Because when you run that C++ loop and you double your input size from 10 to 1,000 and you just watch the execution time spike into infinity on your monitor, you are not watching inefficient code.
You're watching a fundamental law of nature assert itself.
Exactly. The mathematical barriers to solving P versus NP are just immense. Our abstract frameworks, like Turing machines, they just keep hitting theoretical limits. I mean, for decades, the absolute brightest minds on the planet have tried to mathematically prove that P does not equal NP, and every single proof method has failed.
But wait, if classical computers fail so spectacularly at combinatorial search, isn't our entire global banking system built on that exact weakness?
It is.
Doesn't RSA encryption basically rely on the fact that computers can't search for the prime factors of massive numbers?
That is the exact linchpin of global security, yes.
Which means to understand our own digital security and why it might literally be on the verge of collapse, we have to understand the fundamental architecture of prime numbers.
Right.
Which perfectly transitions us away from code and directly into this 160-year-old mathematical enigma, the Riemann Hypothesis.
Yeah, it's unavoidable. To understand why cryptography holds up, we have to examine the distribution of primes. Prime numbers divisible only by one and themselves, they are basically the atoms of mathematics.
But locally, when you look at them on a number line, they appear completely chaotic.
Completely chaotic.
They look like static on a radio. 2, 3, 5, 7, 11. As you get into the millions or billions, the gaps between them are just entirely unpredictable. You can't predict when the next pop of static is going to happen.
And that chaos frustrated mathematicians for centuries, literally centuries, until Leonhard Euler in the 18th century, and then later Bernhard Riemann in 1859, developed what is known as the Riemann Zeta Function.
Now, let's avoid reading the raw equations aloud here, because honestly, nothing kills an audio deep dive faster than reciting Greek letters and infinite sums.
Fair point, fair point.
Conceptually, what is this function actually doing to that radiostatic?
Okay, so think of the zeta function as a mathematical prism. Euler made this staggering discovery with his product formula. He proved that if you take all the smooth, predictable, continuous waves of standard calculus, and you multiply them together in a very highly specific way, they perfectly align with the jagged, chaotic, unpredictable jumps of the prime numbers.
Oh, wow.
Yeah, he built an unbreakable bridge between smooth geometry and choppy arithmetic.
So you run the random radiostatic of the primes through this prism, and suddenly you see that the static isn't random at all. The prism reveals a hidden underlying radio frequency that dictates exactly where those primes have to exist.
Exactly. And that frequency is defined by what Castillo calls the zeros of the zeta function. When you plug numbers into this massive function, most of the time it just spits out a messy, complicated result. But for very specific magical inputs, the entire massive equation cancels itself out and spits out exactly zero.
And Castillo's text emphasizes that these zeros aren't just quirks of the math, right? They're really important.
Oh, they are everything. They are the literal structural features that govern the prime numbers. They are the harmonic frequencies controlling the static we talked about. And the Riemann hypothesis, which is essentially the holy grail of modern mathematics, it asserts that every single one of these important zeros lies on one perfectly straight vertical line in the complex mathematical plane.
The critical line.
The critical line, exactly.
The way Castillo explores this is so beautiful because he refuses to just leave it in the abstract. He uses computational visualization to literally map this out. So imagine you are walking on a 3D topographical map. The inputs of the function are your GPS coordinates.
Right, latitude and longitude.
Exactly. And you are looking for the exact valleys where the elevation drops to sea level to zero.
And because we are dealing with complex numbers here, you have a real part and an imaginary part. So Castillo uses contour plots to draw a line everywhere the real part is zero and another line everywhere the imaginary part is zero.
And where those two lines cross on the map,
You have found a zero.
it turns abstract theory into an observable physical landscape. You can literally see the deep analytic structure of primes. And this structure governs all sorts of bizarre prime phenomena, right? Like Mersenne primes and twin primes.
Absolutely. A Mersenne prime is a massive prime number generated by taking 2 to the power of a prime and subtracting 1.
They're the ones that are super rare, right?
Very rare. So rare that when you hear a news story about a computer discovering a new largest known prime, it is almost exclusively a Mersenne prime.
And twin primes.
Twin primes are pairs that sit right next to each other, separated by only one even number, like 29 and 31. The zeta function's frequencies dictate the emergence of these massive, isolated Mersenne primes and also these tightly clustered twin primes.
Okay, let's connect the dots here and raise the stakes back up. Because classical cryptography relies entirely on the fact that primes are easy to multiply together to create a massive lock, but practically impossible to pull apart, to factor once they are combined.
Right, because pulling them apart requires combinatorial search.
Exactly. And the P-Visas NP wall proves that our classical processors will take 40 quintillion years to search through that complexity.
So we feel safe. The banking system feels safe.
Right. But what if we don't try to chip away at the wall with a classical hammer? What if we change the fundamental physics of the machine itself?
Which brings us right to the threshold of quantum computing. This is where we abandon the classical architecture that hits the exponential wall entirely, and we start exploiting the bizarre laws of subatomic reality.
Now, we all know classical bits are basically just binary locks. They are switches that are strictly off or strictly on, 0 or 1. But Castillo points out, the moment you introduce a qubit, a quantum bit, you are no longer dealing with binary states.
Yes, no, you are dealing with the superposition.
Break that down for us.
Yeah, so a qubit can exist in a complex blend of both 0 and 1 simultaneously. The author writes out the quantum state equation, and what stands out isn't really the variables, it's that it functions like a recipe.
A recipe.
Yeah. You have 2 ingredients, the 0 state and the 1 state. The variables attached to them, which are called probability amplitudes, are basically just the exact percentages of how much of each ingredient is currently swirling together in the mixing bowl.
But there is a hard physical limit to that mixing bowl. The text calls it the normalization constraint.
Right.
The squares of those two percentages must always add up to exactly 1 or 100%. Why is nature so strict about that?
Because of the violent reality of quantum measurement. While the qubit is unobserved, it exists in that swirling mathematical superposition. But the moment you look at it, the moment the system physically measures the qubit, the quantum state collapses.
It can't stay a blend.
No, it cannot remain a blend in the physical world. It must snap into being a definite 0 or a definite 1. The amplitudes dictate the probability of which state it will snap into. But since it has to be one or the other, those probabilities must total 100%.
Okay, stop right there. Because I have to ask the obvious question. I hear this and my brain immediately says, so a qubit isn't a magical state of guaranteed information. It's just a heavily weighted coin flip.
Right, that's a common reaction.
How does making a computer's memory probabilistic and fuzzy actually make it faster? That just sounds like a recipe for constant errors, not a master key for exponential math.
It is the most common and honestly most vital misunderstanding of quantum mechanics. The speed does not come from a single qubit being fuzzy or uncertain. The speed comes from how multiple qubits scale and interact exponentially.
Explain that.
Okay, if you have 50 classical bits, they can only hold one single value at any given microsecond. It is a single sequence of 50 zeros and ones.
Right. One state out of trillions of possibilities.
But if you have 50 qubits in superposition, they aren't just holding 50 fuzzy values. They are holding a superposition of 2 to the 50th power values simultaneously.
Whoa.
Yeah, they are physically representing over a quadrillion states in the computational space at the exact same time.
But if measuring them forces them to collapse randomly into just one of those quadrillion states,
Right.
how do you ever get the right answer out of the machine?
And that is where the absolute genius of quantum algorithm design comes in. It relies entirely on wave interference. The text uses an incredibly elegant music and wave analogy to explain this.
Oh, like noise-canceling headphones.
Yes.
Think about it. Noise-canceling headphones listen to the roar of an airplane engine, and they generate the exact opposite sound wave. The two waves physically collide in the air, they cancel each other out, and you just hear silence.
That is destructive interference. Exactly. The probability amplitudes in our quantum recipe act exactly like those waves. A quantum algorithm is intricately choreographed so that the probability amplitudes of the wrong answers, the incorrect paths through the maze, interfere destructively.
They act like the noise-canceling headphones.
Right. They wave cancel each other out, driving the probability of the wrong answers down to absolute zero.
But simultaneously, the amplitudes of the right computational paths are engineered to interfere constructively, like two synchronized ocean waves slamming together to create a massive tsunami. The correct answers reinforce and amplify each other.
So when the algorithm finishes and you finally perform the measurement, the system doesn't just collapse randomly like a coin flip. You have manipulated the subatomic waves so heavily that the system has an overwhelmingly massive probability of collapsing precisely onto the correct answer.
You didn't search the paths one by one.
No, you evaluated all quadrillion paths simultaneously, let the wrong ones destroy each other, and measured the sole survivor.
That is genuinely reality-breaking. And the physics get even stranger when the author brings in quantum entanglement.
Oh, entanglement accelerates this entirely. It is the phenomenon where two or more qubits become fundamentally linked, acting as a single mathematical entity regardless of physical distance. So if you entangle qubit A and qubit B, they share a single quantum state.
Which means if I take qubit A to the moon and I leave qubit B here on Earth, the exact nanosecond I measure qubit A and force it to collapse, qubit B instantly collapses into a correlated state.
Instantly.
No radio signal travels between them. It completely defies the speed of light.
Which is exactly why Albert Einstein famously derided it as spooky action at a distance. He just couldn't accept that the universe actually operated that way.
But it does.
It does. And in a quantum computer, that spooky action is essentially the wiring. It allows qubits to share information and correlate probabilities instantaneously across the processor, making those wave interference algorithms drastically more powerful.
So, bringing us all the way back to our invisible wall, does quantum computing finally solve P vs NP? Does it give us the master key?
Well, not universally, no. Quantum computers do not magically solve all NP-complete problems instantly. Instead, they basically carve out a brand new realm of computation called the BQP complexity class.
BQP, bounded error quantum polynomial time.
Yes. BQP represents the specific domain of problems that a quantum computer can solve efficiently. It easily swallows all the easy classical problems, but its true power is that it reaches out and consumes specific mathematical problems that are currently trapped behind the classical exponential wall.
And this leads us directly to the terrifying climax of Castillo's synthesis, the quantum earthquake.
Yes.
Because the specific mathematical problem that BQP consumes is prime factorization.
Exactly. Peter Shor developed a quantum algorithm that explains the underlying wave structure of primes, the very harmonic frequencies we discussed with the Riemann Zeta function, to factor massive numbers exponentially faster than any classical machine ever could.
I mean, we moved past simple classical ciphers centuries ago. The text mentions the Roman Caesar cipher, where you basically just shift the alphabet a few letters.
Right.
And those were weak because they leaked structural patterns. So modern public key cryptography, which is the foundation of our entire digital existence, was built specifically because we needed the math of primes to protect us. We assumed the P vs NP wall would guard those primes forever.
But a quantum computer simply phases right through that wall. Shor's algorithm, running on a sufficiently powerful quantum computer, will braid RSA encryption, elliptic curve cryptography, and nearly every public key system currently securing our databases, financial grids, and military communications.
When you start talking at a tech-driven apocalypse that requires us to update literally every computer on Earth, a very specific historical parallel comes to mind.
Y2K.
Yes, the text compares the looming quantum threat to the year 2000 bug Y2K. And I have to push back here because culturally, Y2K is basically treated as a punchline.
I know, it really is.
People think it was a massive hoax because the clocks rolled over to 2000 and the lights just stayed on. So is the quantum threat just another overblown panic to sell consulting hours?
That cultural memory is deeply, deeply flawed, and Castillo uses historical data to correct it here. People think Y2K was a hoax because the lights stayed on. But that is like saying a Category 5 hurricane was a hoax because you spent 2 weeks boarding up your windows and your house didn't shatter.
That's a great point.
Y2K was a profound systemic risk to global infrastructure that relied on legacy date codes.
Right. The system would have read the year 00 as 1900, creating negative interest rates, deleting records, and crashing scheduling software everywhere.
The planes didn't fall out of the sky because the world spent over $300 billion aggressively auditing code. Armies of programmers meticulously replaced legacy hardware and rigorously patched systems for years before the deadline. It was a crisis averted through unprecedented global investment, not a crisis fabricated.
And the assertion here is that we need exactly that level of panic and that level of investment right now for PQC, post-quantum cryptography.
Yes. We absolutely cannot wait for a 4,000 qubit machine to come online before we react. We must invent and implement new mathematical locks that even quantum wave interference cannot pick. And we have to migrate the entire global banking and intelligence apparatus to those locks immediately.
But Castillo doesn't just leave us with doom and gloom, which I appreciate. He outlines this quantum capabilities roadmap that shows this technology isn't just a lockpick. It is a fundamental evolution of artificial intelligence. We aren't just breaking codes. We are simulating reality natively.
The roadmap is a staggering vision of the near future, really. It begins with the OPT-01 phase, which is optimization algorithms. If you can use quantum interference to find the optimal path through a chaotic system, you revolutionize logistics, manufacturing, and global finance almost overnight.
Then the roadmap moves into MLO2, accelerated machine learning. We are talking about actual quantum neural networks. Instead of an AI reading data sequentially, a quantum AI evaluates millions of parameters simultaneously through superposition. It learns exponentially faster.
Which feeds directly into the VIS-03 data 04 phases. Quantum algorithms excel at high-dimensional pattern detection. They can parse massive visual streams and unimaginable data sets to find deep, invisible correlations that classical computers would need a millennia to even notice.
And the pinnacle of this roadmap, ARCH-05, is where it gets truly sci-fi, creating entirely new AI architectures designed from the ground up for a quantum environment, specifically to solve chemistry and physics.
Think about drug discovery. A classical computer really struggles to simulate how a complex molecule folds because the molecule operates on quantum mechanics while the computer operates on binary code.
It's a translation error.
Exactly. A quantum computer simulates quantum mechanics natively. It acts exactly like the molecule. We could design targeted cures for diseases in an afternoon. We could simulate new battery materials or carbon capture mechanisms down to the actual subatomic level.
It fundamentally changes our relationship with the physical world. And it brings us full circle on the incredible journey we've taken today. We started by driving a supercar into the invisible wall of exponential growth. We saw how P versus NP proves that classical logic is mathematically doomed when searching through complexity.
We realized that our security is built entirely on that classical failure, which forced us to look at the harmonic, wave-like structure of prime numbers through the prism of the Riemann Zeta function.
And finally, we saw that the only way to bypass that classical wall is to build a machine that harnesses the bizarre, probabilistic reality of subatomic physics, using superposition, wave interference, and entanglement to achieve the impossible. It is a paradigm shift that demands a Y2K-level global mobilization to protect our data, but it also opens the door to an absolute golden age of artificial intelligence.
And, if we step back and look at the absolute largest picture possible, Castillo's synthesis leaves us with a truly staggering realization. Well, we've spent this entire time talking about how our human-made classical computers hit an absolute mathematical wall. They freeze. They would take 40 quintillion years to calculate a complex molecular interaction.
Right.
But the universe just does it. The molecules in your body are effortlessly interacting right now. The stars are burning. The universe calculates those impossibly complex variables instantaneously, simply by existing. The only way we can break through our classical limits is to abandon our human-invented binary logic and build a machine that directly mimics the fundamental physical laws of that universe.
Which raises a really wild question for you to mull over long after you finish this deep dive.
Yeah.
If the universe's natural state effortlessly processes, interferes, and resolves quantum probabilities that would take our classical supercomputers billions of years to even begin to simulate, does that mean the universe itself is fundamentally just a massive, ongoing quantum computation? And if it is, what exactly is it trying to compute?